The universe should be empty. Completely, totally empty. 13.8 billion years ago, the Big Bang created matter and antimatter in equal amounts. When they met, they destroyed each other, every single particle. Gone. Pure light. That is what the math says. So why does anything exist? Why do you exist? We are about to go from the first fraction of a second after the Big Bang, through underground particle colliders, into beams of ghostly particles fired through solid rock, and all the way to a discovery that just shook science in 2025. If this blows your mind, subscribe and drop a like. Prepare yourselves. We begin. The math said nothing should exist. 13.8 billion years ago, the universe exploded into being from a point smaller than anything you can picture. Smaller than an atom. Smaller than a grain of dust. In that first instant, temperatures reached levels so extreme that energy itself started converting into something physical. Into the raw building blocks of everything. Physics had a rule for how that worked. Every time energy created a particle of matter, it had to create an equal partner, a mirror twin. One piece of matter, one piece of antimatter. Always in pairs, always perfectly balanced. The universe was running a strict accounting system, and the books had to balance down to the very last particle. So they did. For every electron born in that chaos, an anti-electron appeared beside it. For every proton, an anti-proton. Billions upon billions of pairs, flooding into existence in the first fractions of a second. The universe was filling up fast. Then the twins found each other. When a matter particle and its antimatter partner collide, they do not bounce off each other. They do not slow down. They vanish. Both of them instantly converted into a burst of pure energy. Light. Just light. The collision is total, complete. There is nothing left behind. In those first moments, the universe was running this process on a scale too enormous to picture. Particles smashing into their twins across every inch of rapidly expanding space. A war of annihilation happening everywhere at once. Matter destroying antimatter. Antimatter destroying matter. The energy released was so intense it filled all of space with blinding radiation. The math said this would go all the way to zero. Every matter particle would find its twin. Every antiparticle would find its match. The books would balance. The destruction would be complete. And the universe would be left with nothing but a vast, silent ocean of fading light. No atoms, no stars, no planets, no you. That is what the equations predicted. That is not what happened. Something went wrong. Or maybe something went right, depending on how you look at it. For reasons that science has been chasing for 60 years, the balance was off. By a tiny amount. An almost invisible difference. For every 1 billion pairs of matter and antimatter that destroyed each other, one single particle of matter survived. Just one. Alone, with no twin, with nothing coming to erase it. One particle out of a billion. That sounds like almost nothing, and compared to what was destroyed, it was almost nothing. But the universe is so unimaginably large that even a tiny fraction of something enormous is still enormous. Those surviving particles, that microscopic leftover, became everything. Every galaxy you have ever seen in a photograph. Every star in the night sky. Every mountain, every ocean, every cell in your body. All of it built from particles that had no right to survive. Scientists call this the Baryon asymmetry problem. The name is dry. The reality is staggering. The universe broke its own rule. Its own fundamental law of perfect balance. And nobody can fully explain why. Here is the thing that makes this even stranger. The rule it broke was not a small one. It was written into the deepest layer of physics. Symmetry. The idea that matter and antimatter are two sides of the same coin. Perfectly equal. Perfectly interchangeable. The universe was supposed to honor that completely. It did not. And that tiny act of rule breaking is the only reason anything exists at all. The only reason you are here right now, listening to any of this. The question is, what caused it? And finding that answer starts with understanding exactly what antimatter is, and why it is one of the most dangerous things the universe has ever produced. Antimatter sounds like something from a movie. It is real. Completely, scientifically real. Physicists discovered it, created it, and have been trapping it in laboratories for decades. It is one of the most well-tested ideas in all of science, and it is stranger than any movie has managed to make it look. Here is the simplest way to understand it. Every particle of matter that exists has a twin. An exact copy, identical in almost every way. Same mass, same size, same behavior under most forces. The only difference is the electrical charge is flipped. Where a regular electron carries a negative charge, its antimatter twin, called a positron, carries a positive one. Where a proton is positive, an antiproton is negative. Flip the charge. Everything else stays the same. That is antimatter. Now, here is where it gets dangerous. The moment an antimatter particle touches its matter twin, both of them disappear. Completely. The mass of both particles converts directly into energy. Pure, raw energy released in a flash. Nothing left behind, no debris, no ash. Total conversion. Einstein's famous equation connects mass and energy, and that equation tells us that even a tiny amount of mass, when fully converted, releases an enormous amount of energy. A single gram of antimatter meeting a single gram of matter would release energy equal to an atomic bomb. A full gram. That is less than a paperclip. CERN, the massive physics lab straddling the border between France and Switzerland, actually creates antimatter in tiny, almost impossibly small quantities to stop it from instantly destroying itself on contact with the walls of the container. Scientists suspend it inside magnetic fields. A cage of invisible force, holding the antimatter in the center of a vacuum chamber, never letting it touch a single atom of regular matter. If the power cuts out, the antimatter hits the wall and vanishes in a flash of energy. The amount they make is so small the explosion would barely warm a cup of coffee. But the principle is the same. Antimatter is not hypothetical. It is sitting in a laboratory right now, suspended in a magnetic trap, waiting. Here is the part most people never hear. Antimatter is also falling on you from space. Cosmic rays, high-energy particles fired out by distant stars and explosions across the galaxy slam into Earth's atmosphere every day. Some of them are positrons, antimatter electrons, raining down from the sky. Your body intercepts them constantly, and you feel nothing, because they collide with atmospheric particles long before they reach the ground. And your hospital almost certainly uses antimatter to scan human brains. Positron emission tomography, the brain scan technology doctors use to study tumors and track disease, works by injecting a small amount of a substance that emits positrons into the body. Those positrons travel a tiny distance, meet electrons in nearby tissue, annihilate, and release energy in a precise direction. Detectors surrounding the patient catch that energy and map exactly where it came from. Doctors see inside the brain using controlled antimatter annihilation. Antimatter is not exotic, it is medical, it is astronomical, it is in laboratories on Earth right now. So if antimatter is real, and if it destroys matter on contact, and if the Big Bang created both in equal amounts, the total destruction the math predicted should have happened. Every particle erased. Every gram of matter annihilated. Something stopped that from happening. Some force, some process, some tiny flaw in the symmetry between matter and antimatter tipped the balance just enough. Just one particle in a billion. What that flaw was and how deep it runs is where this story gets genuinely strange. You cannot picture how fast it happened. The first second after the Big Bang is not one moment. It is billions of moments stacked inside each other. Physicists break it down into fractions so small they have no name in everyday language. 1/1,000,000th of a second, 1/1000,000th, 1/1,000,000,000th. Each slice of time holds a completely different universe, running through transformations at a pace that makes all of human history look like a single, slow breath. In the very beginning, there were no particles at all, just energy. Pure, concentrated, almost incomprehensibly hot energy packed into a space you could hold in your hand. Then, that space began to expand. And as it expanded, it cooled. And as it cooled, the energy started doing something remarkable. It started taking shape. Energy converts into mass. Einstein told us that. When the universe was hot enough, that conversion ran constantly, in every direction, all at once. Energy snapping into particles and antiparticles, pairs popping into existence out of pure heat. The universe was essentially a machine for building particles, running at full speed. For the first tiny fractions of a second, the temperature was so high that even the heaviest particles could form. Massive, unstable things that exist today only briefly inside particle colliders. Back then, the universe was making them constantly, in vast numbers, and they were immediately destroying each other and forming again. Matter and antimatter flickering in and out of existence so fast the whole process looked more like a boiling liquid than a structured event. Then, the universe kept expanding. It kept cooling. And as the temperature dropped, the heaviest particles stopped forming. The energy was no longer hot enough to make them. They annihilated their partners and did not get replaced. Then the next heaviest particles followed. Then the next. Layer by layer, the most massive things in the universe were wiped out in waves of mutual destruction. Each wave left behind only light, only energy, as the matter and antimatter cancelled each other out. The universe was getting emptier with every passing microsecond, thinning out, cooling down, losing mass to light in an ongoing chain of annihilation. This is the moment that should have ended everything. As the temperature fell far enough, even the lightest particles, the protons and electrons that make up atoms today, reached their annihilation point. Their antimatter twins were right there, equal in number. The destruction should have been total. It was almost total. That word matters enormously. Almost. The surviving fraction, 1 in 1,000,000,000, did not escape through some dramatic event. There was no force field, no cosmic shield. The asymmetry was built in from the start, baked into the rules of how matter and antimatter behaved during those first fractions of a second. Something in the physics of that moment treated matter and antimatter just slightly differently. Enough to leave a residue, a leftover. The annihilation still happened on a massive scale. The light produced by all those collisions flooded the universe and has been traveling ever since. Stretched by the expansion of space into longer and longer wavelengths. Cooling over billions of years into something scientists can detect today with the right instruments. That ancient light is still out there, surrounding us on all sides, carrying a record of the destruction that almost erased everything. And what it tells scientists about those first moments is simultaneously the strongest clue and the deepest mystery in all of physics. That clue has a name, and it changes how you understand the sky. The annihilation produced the loudest event in the history of the universe. There was no sound in space, but if you measured raw energy output, the destruction of matter and antimatter in the first seconds after the Big Bang dwarfs every explosion, every supernova, every collision that has happened in the 13 billion years since. The universe lit itself up from the inside, converting mass into radiation on a scale nothing has ever matched. Every pair that collided released energy moving at the speed of light in two opposite directions. Two photons fired outward, carrying the mass of both particles converted perfectly into light. Across the entire volume of the early universe, this was happening simultaneously in every cubic inch of space. The universe was not just bright, it was nothing but brightness. A sea of high-energy light with nowhere to go except outward, carried by the expansion of space itself. Picture a room packed wall to wall, floor to ceiling, with fireworks all going off at exactly the same instant. Now, make that room the size of the entire observable universe. Now make every firework the result of two particles erasing each other from existence. That is approximately what the first second looked like. Translated into something a human mind can approach. The surviving particles, those 1 in a billion leftovers, were floating inside this chaos, surrounded by the light of their destroyed counterparts. Outnumbered by photons by a ratio of 1 billion to 1, for every surviving particle of matter, there were 1 billion particles of light produced by the annihilation of particles that did not make it. That ratio still holds today. For every single proton or neutron in the observable universe, there are roughly 1 billion photons. 1 billion. Scientists have measured this. It is one of the most precisely confirmed facts in cosmology, and it is a direct record of the destruction that happened in those first seconds. The light outnumbers the matter by exactly the ratio you would expect if almost all the matter was destroyed and a tiny fraction survived. The universe carries its own crime scene evidence. As the universe expanded over the following thousands of years, that light stretched. The expansion of space pulls wavelengths apart, shifting light from high energy toward lower energy. The intense gamma radiation of the early annihilation slowly cooled. Over hundreds of thousands of years, it became lower energy. Less intense, but still everywhere. Still filling all of space. Then, about 380,000 years after the Big Bang, the universe cooled enough for the surviving matter particles to finally combine into the first atoms. The light, which had been bouncing off the dense particle soup constantly, suddenly had room to travel freely. It streamed outward in all directions, freely, unobstructed. The universe became transparent for the first time. That moment of release is fossilized in the sky. The light from that instant, now stretched by 13.8 billion years of cosmic expansion into invisible microwaves, still surrounds Earth on all sides. Scientists detected it in the 1960s, at first by accident, when they noticed a faint background noise coming equally from every direction in space. They called it the cosmic microwave background. Your old analog television, tuned to a channel with no signal, would show a faint static. A small percentage of that static came from this ancient light. The echo of the greatest destruction event in history, still arriving on Earth, carrying the fingerprint of a war that ended billions of years before the sun existed. That fingerprint is not just a curiosity, it is a measuring tool. And what scientists measure inside it points directly at the mystery of why the asymmetry happened at all. Physics runs on symmetry. That might sound abstract, but symmetry in physics means something very specific. It means that if you change certain things about a situation, the outcome stays the same. Flip the charge of every particle in a reaction. Mirror the whole thing left to right. Run time backward. If the physics is truly symmetric, none of those changes should matter. The same rules apply. The same results come out. For most of the 20th century, scientists believed the universe obeyed a specific version of this. They called it charge parity symmetry. The idea was elegant and clean. Swap every particle for its antimatter partner, changing its charge, then mirror the entire event in space, flipping left and right. If you did both of those things at once, the physics should look completely identical. Matter and antimatter were supposed to be perfect mirrors of each other in every meaningful way. If that symmetry held perfectly, The Big Bang would have produced matter and antimatter in truly identical proportions. They would have destroyed each other completely, and the universe would be empty. The symmetry, if real and perfect, is a death sentence for existence. So the symmetry had to be broken. Something in the early universe had to treat matter and antimatter differently. A gap, however small, in how they behaved. That gap, whatever caused it, is the reason you exist. Physicists gave this gap a name. They call it CP violation. CP for the charge and parity that was supposed to be symmetric. Violation for the fact that nature broke the rule. Proving CP violation existed was the central challenge of particle physics for decades. Because you cannot just look at the sky and see it. You have to recreate the conditions where it shows up. You have to smash particles together at enormous speeds and watch how the debris behaves. You have to compare matter reactions to antimatter reactions and find the difference. A tiny, specific, measurable difference. For years, nobody found it. The symmetry seemed to hold. Every experiment confirmed that matter and antimatter obeyed the same rules, decayed at the same rates, and behaved identically in every test physicists could design. The universe appeared to be following the rules that should have made it empty. Then, a small team of scientists in the United States stumbled into something that changed everything. They were studying a type of particle called a kaon. They were not specifically hunting for CP violation. They were testing something else entirely, and what they saw in the data stopped the experiment cold. The kaons were not behaving symmetrically. Matter kaons and antimatter kaons were decaying at slightly different rates. The difference was tiny, barely a fraction of a percent. But it was real, and it was reproducible, and it could not be explained by any known error. The symmetry was broken. CP violation was real. That discovery, confirmed in 1964, won a Nobel Prize. It proved that the universe does treat matter and antimatter differently. A fundamental crack ran through the supposed perfection of physical law. The problem was the size of the crack. It was far too small. Scientists ran the numbers. The level of CP violation found in kaons could account for an almost invisible fraction of the matter, antimatter imbalance that produced the universe. You would need a violation thousands of times larger to explain why we are here. So the crack existed. But it was nowhere near big enough. The answer had to be hiding somewhere else, in a different particle, a deeper layer of physics, a rule not yet discovered. The search for that deeper crack was about to take science somewhere far stranger. Stop and picture the scale of what survived. One particle. For every 1 billion pairs that destroyed each other, one particle of matter remained. That ratio is so extreme it is almost impossible to hold in your mind. Imagine a stadium packed with 1 billion people, all of them paired up and walking toward each other. Every pair collides and disappears, and when the stadium is finally empty, one single person is still standing there, alone, in the center of the field. That is the particle that built the universe. Now scale that stadium up to the size of the early universe. Run the same process in every cubic inch of space, simultaneously. The number of particles involved is so vast that even the 1 in a billion survivors add up to an almost uncountable quantity. And every single atom in the observable universe, in every star, in every galaxy, in your body right now, is descended from one of those survivors. Every proton in your bones was there. Every electron in your brain. Every atom in every cell of your body carries a lineage stretching back to those first seconds, when it beat the odds and escaped the annihilation. You are, in a very literal sense, made of the leftovers of a war. That surviving fraction is called baryonic matter. Baryons are particles built from 3 quarks, the fundamental components of protons and neutrons. All the matter you can see, touch, weigh, or measure anywhere in the observable universe is baryonic matter. Stars, planets, gas clouds, asteroids, your own body, all of it built from the Baryons survivors. And here is something that catches most people off guard. All of that, everything you can see or detect, makes up only 5% of the total content of the universe. 5%. The rest is dark matter and dark energy, invisible and still poorly understood. The baryonic matter we can observe, the stuff we know, the stuff we are made of, is the minority. So the universe started with a perfect balance that should have produced zero matter. The imbalance produced a tiny fraction. And that tiny fraction, after 13.8 billion years of gravity pulling things together, produced galaxies, stars, planets, oceans, and you. A universe built on a rounding error. The surviving particles did not immediately form atoms. First, they drifted in a hot soup of quarks and electrons. The universe was still too hot for them to combine. It took about 1 second for protons and neutrons to form from the quarks. Then it took about 3 minutes for those protons and neutrons to lock together into the first simple atomic nuclei, mostly hydrogen and helium. But it still took 380,000 years for the universe to cool enough for electrons to join those nuclei and form complete atoms. 380,000 years of drifting particles, slowly cooling, slowly organizing. And at the end of that stretch, the first atoms appeared. The building blocks were finally ready. All of them survivors. All of them descendants of the 1 in a billion that made it through the fire. The universe spent the next 13 billion years building everything else from those survivors. Stars fused the light atoms into heavier ones. Those stars exploded and scattered the heavy atoms across space. New stars formed from the debris, planets grew around them. And eventually, on at least one of those planets, the atoms organized into something that started asking where they came from. The question now is what made those survivors survive. And the answer, it turns out, is buried in the smallest things physicists have ever found. Picture a sky with nothing in it. No stars, no galaxies, no dim glow of distant nebulae, no planets, no dust, no atoms, just a faint cooling bath of microwave radiation, stretching in every direction for billions of light years, getting thinner as space expands, growing colder with every passing eon, no structure anywhere, no gravity pulling anything together because there is nothing to pull. That is the universe that should exist. That is the outcome the mathematics of the Big Bang demands if matter and antimatter were truly equal. The cosmic microwave background would still be there. The annihilation light, now stretched into invisible microwaves, would still fill all of space. But there would be nothing else, no source of new light, no fusion reactions in stellar cores, no planets warming under a local star. Just the fading echo of an event that erased itself, growing colder and more diffuse as the universe expanded forever into darkness. This is the universe the physics textbooks of the early 20th century almost described. Before scientists realized something had gone wrong with the symmetry, or rather, something had gone right. The key detail is this: matter does more than just exist. It clusters. Gravity pulls particles together over time, gathering gas into clouds, clouds into stars, stars into galaxies. But gravity needs something to work with. It needs mass. It needs matter already present, unevenly distributed, so it can start pulling clumps together. In a universe with only radiation and no matter, gravity has nothing to grip. Light does carry energy, and energy does interact with gravity, but diffuse radiation spread evenly across space produces no structure. Nothing to pull together. Nothing to collapse into density. The expansion of space wins every time. Everything spreads out and thins forever. The universe we live in is different because matter existed in uneven patches. The tiny quantum fluctuations in the early universe, Microscopic variations in density gave gravity a foothold. Matter fell towards the denser regions. Over hundreds of millions of years, the first stars ignited. Then galaxies formed around them. Then clusters of galaxies. The large-scale structure of the universe grew from those seeds. All of that required matter to be there in the first place. Specifically, baryonic matter, protons and neutrons, the survivors. Remove the survivors, and you remove every structure in the universe. Every star that has ever burned, every supernova that has ever scattered heavy elements across space, every planet that has ever formed in a habitable zone around a stable star, every ocean, every atmosphere, every chemical reaction complex enough to produce life. The 1 in a billion asymmetry did not just save some particles, it saved the entire process by which complexity is possible. Without it, the universe would reach a state of maximum sameness and stay there. Expanding, cooling, thinning, until the last photon is so stretched by the expansion of space that it carries almost no energy at all. The universe heading toward that outcome is not dramatic. It simply fades, uniformly, silently, without any structure to mark the passage of time. The universe we live in, the one with stars and planets and the fact that anything interesting has ever happened anywhere, exists because a tiny violation of symmetry produced a surplus of matter so small it should barely matter. Yet, here we are. Evidence that even a rounding error can build a cosmos. And somewhere buried in the rules of physics, the mechanism that caused that violation is still hiding. Scientists have found pieces of it, but the full picture is still missing. One piece they found was in the smallest particle lab ever built. Watching particles decay in a way that bent the rules. Right now, coming from every direction in space, an ancient signal is passing through you. It has been traveling for 13.4 billion years. It started as high-energy radiation, born from the annihilation of matter and antimatter in the first seconds of the universe. Over all that time, as space expanded, the wavelength of that light stretched longer and longer. It shifted from intense gamma radiation to X-rays to visible light to infrared to microwave. By the time it reaches you today, it is invisible, carrying almost no energy, and arriving equally from every point in the sky. This is the cosmic microwave background, the leftover glow of the Big Bang. And it is the single most important piece of evidence scientists have for understanding what happened in those first moments. In the late 1950s, 2 engineers at Bell Telephone Laboratories in New Jersey were building a large radio antenna designed to communicate with early satellites. They kept picking up a persistent background noise in their data. A faint hiss, equally strong in every direction, that they could not eliminate. They checked the antenna. They chased pigeons out of the dish and cleaned away their droppings. They recalibrated everything. The noise remained. A few miles away, physicists at Princeton University were building a detector specifically designed to find exactly that signal. They had predicted it from theory. The Bell engineers heard it by accident first, and the Princeton team helped explain what it was. The discovery earned a Nobel Prize. What the cosmic microwave background reveals is extraordinary. The temperature of this background radiation is almost perfectly uniform across the entire sky. Everywhere you point a detector, the temperature reads the same. 13.7 degrees above absolute zero, which is the coldest possible temperature in the universe. Almost perfectly uniform. Those 2 words are doing enormous work. The background is not perfectly smooth. There are tiny fluctuations in temperature, variations smaller than 1 part in 100,000, rippling across the sky like the faintest possible wrinkles. Those wrinkles are the seeds of everything. They are the slight unevenness in the early matter distribution that gravity later amplified into galaxies and stars. Scientists have mapped those fluctuations in extraordinary detail using space-based telescopes. The pattern of the ripples tells them the age of the universe, its composition, how fast it is expanding, and the total amount of matter and dark matter it contains. The cosmic microwave background is the most detailed picture of the early universe that science has ever produced. But hidden inside it is also a record of the asymmetry. The ratio of photons to matter particles, 1 billion to 1, is encoded in the background. The total energy of the radiation reflects the total destruction. The number of surviving matter particles shows up as the 5% baryonic content of the universe. All of it written in microwaves, all of it still present. Still passing through you right now, every second, at the speed of light from every direction. The ancient signal carries the answer. Scientists are still learning how to read it, but reading it requires understanding the particles involved in that original asymmetry, their structure, their behavior, their hidden rules. And the deeper scientists look into those particles, the stranger the rules become. In physics, some rules feel unbreakable, not because scientists decided they should be, but because every experiment ever run seemed to confirm them. They showed up in every calculation. They survived every test. And the symmetry between matter and antimatter was one of those rules. For the first half of the 20th century, it sat at the foundation of physics like a load-bearing wall. Touch it, and everything collapses. The symmetry had a specific shape. Think of it as two operations you could perform on any physical event. The first, swap every particle for its antimatter counterpart. Change every negative charge to positive, and every positive to negative. The second, mirror the entire event in space. Flip left and right, like holding the reaction up to a glass. Do both of those transformations together, and the physics should look identical. Same outcome, same probabilities, same rates of decay. Matter and antimatter, reflected and swapped, behave in exactly the same way. That was the prediction. That was the rule. Physicists called it CP symmetry, charge and parity symmetry, and it was elegant. If it held perfectly, it meant the universe had a deep and beautiful balance, written into its laws. Matter and antimatter were truly equal, truly interchangeable, two sides of the same coin. The problem is that a universe with perfect CP symmetry cannot exist. The math is clear. If matter and antimatter behave identically in every way, they produce identical amounts during the Big Bang, and they destroy each other completely. Our universe, the one we are sitting inside, is a direct contradiction of perfect CP symmetry. So either the symmetry was broken, or scientists were missing something enormous. By the early 1960s, some physicists had begun to suspect the symmetry was not as perfect as it looked. The tools to test it had improved. The particle accelerators could produce enough exotic particles to run meaningful experiments, and a small team working at Brookhaven National Laboratory in New York was about to find what they were looking for, even though they were not quite looking for it. They were studying kaons. A kaon is a particle built from one quark and one antiquark, held together briefly before it decays. It is unstable. It falls apart quickly, and the way it falls apart, the specific products it leaves behind, and the rate at which it does so carries information about the symmetry of the underlying physics. The team watched thousands of kaon decays. They measured the rates carefully. They compared matter kaons to antimatter kaons. And in the data, almost hidden in the statistical noise, they found it. A difference. Small, clear, real. Matter kaons and antimatter kaons were decaying at slightly different rates. The symmetry was broken. Nature treated them differently, if only by a hair. The discovery was stunning, and it raised an immediate and urgent question. If CP symmetry was broken, why was it only broken by such a tiny amount? The imbalance, that produced our universe required a violation far larger than anything the Kaon data showed. Where was the rest of the asymmetry hiding? That question would take decades to even partially answer. And the path to the answer led through the smallest building blocks of all matter itself. It happened in a windowless room on Long Island. The year was 1964. The lab was Brookhaven National Laboratory, a government research facility on the North Shore of Long Island in New York. The scientists involved were James Cronin and Val Fitch, along with their colleagues. They had a particle accelerator, a beam of kaons, and a set of detectors watching for specific patterns in how those kaons fell apart. Kaons are short-lived particles. They form, exist for a brief moment, and then decay into lighter particles. There are different ways they can decay, different combinations of products they can produce. The rates at which each decay mode happens are measurable, and CP symmetry made a clear prediction about those rates. If the symmetry held, matter kaons and antimatter kaons would each decay the same way, at the same rates, producing the same distribution of products. You could swap the matter version for the antimatter version, and the numbers would match exactly. Cronin, Fitch, and their team ran the experiment carefully. They collected data on thousands of kaon decays. They built up the statistics they needed to make a confident comparison. And then they looked at the results. The rates did not match. A tiny fraction of the time, kaons decayed in a way that should have been forbidden if CP symmetry were perfect. The asymmetry was small, less than 1%, but it was consistent, reproducible, real. The team spent months checking their equipment, their methods, and their calculations. They ran the experiment again. The result held. Matter kaons and antimatter kaons were genuinely behaving differently. Nature had a preference, however slight. The supposed perfect mirror between matter and antimatter was cracked. The physics world absorbed this slowly. CP violation was real. The symmetry that was supposed to be unbreakable had broken, and the implications rippled outward in every direction. First, it confirmed that the universe had a built-in bias. Matter and antimatter were not truly interchangeable. The laws of physics treated them differently, at least in some circumstances. That was a genuine, fundamental discovery about the nature of reality. Second, it opened the door to explaining the matter-antimatter imbalance of the Big Bang. If the symmetry could be broken, then maybe the early universe had processes that strongly favored matter over antimatter. Cronin and Fitch had found the principle. The scale of what they found was far too small, but the principle was real. Third, it raised an enormous new puzzle. Why was the violation so tiny? Why 1% or less? The universe needed a much larger imbalance to explain our existence. So either kaons were just the first and smallest example of a much bigger violation hiding somewhere else, or the mechanism behind our survival involved something the Kaon experiment could not reach. Cronin and Fitch received the Nobel Prize in Physics in 1980. Their discovery remains one of the most consequential in the history of science, not because it solved the mystery, but because it proved the mystery was real. The violation existed. The asymmetry was real, and physics now had to find out where the rest of it was hiding. The trail led down into the quarks themselves, the smallest pieces of matter ever discovered, where the rules get strange fast. The physics world celebrated. Then the math arrived. After Cronin and Fitch confirmed CP violation in kaons, scientists did what scientists always do. They took the number, the size of the asymmetry they had measured, and plugged it into the equations describing the early universe. They wanted to know, if the kaon asymmetry was the only source of CP violation in nature, how much matter would survive the Big Bang? The answer came back, and it was deeply unsatisfying. The violation found in kaons was real, but it was so small that it could only account for a fraction of 1% of the asymmetry needed to explain the matter we see today. If kaons were the only source, the universe should still be almost completely empty. The matter we observe, the 5% of the cosmos that makes up everything visible, required a CP violation orders of magnitude larger than anything the kaon experiment revealed. So either the kaon result was just one small piece of a much larger puzzle, or there was something wrong with the entire framework. It turned out to be the first option. Kaons were the first hint. A single crack in the wall. But the wall was big, and cracks could be hiding in many different places. To find them, scientists needed to understand kaons more deeply. And understanding kaons meant understanding what they are made of. Kaons are built from quarks. Quarks are the fundamental particles inside protons, neutrons, and a whole zoo of other particles. They come in different types, which physicists call flavors. Up quarks and down quarks are the most common, forming the protons and neutrons in every atom. But there are also stranger quarks, charm quarks, bottom quarks, and top quarks. Kaons contain a strange quark paired with an up or down antiquark. In the 1970s, a Japanese physicist named Makoto Kobayashi and his colleague Toshihide Masukawa proposed something bold. They suggested that CP violation could arise naturally in the mathematics of quark interactions, and that it would show up most strongly in heavier quarks, specifically the bottom quark, which had not yet been discovered at the time. Their math was elegant. It described a mixing pattern between quarks that naturally produced CP violation as a consequence. The more quark flavors you included in the calculation, the larger the possible violation became. They predicted that the bottom quark would be found, and when experiments studied particles containing it, they would see larger violations than kaons showed. Both predictions came true. The bottom quark was discovered in 1977. Experiments with bottom quarks showed CP violations several times larger than the kaon result. Kobayashi and Masukawa shared the Nobel Prize in Physics in 2008. But the larger violations still were not large enough. Running the numbers again with the bottom quark data, the total CP violation from all known quarks added together still could not produce a universe full of matter. The gap between the theoretical prediction and the observed universe remained enormous. The quark framework was part of the answer. A confirmed, Nobel-winning, experimentally verified part. And it was still not enough. The missing piece had to be somewhere else, in a different type of particle, a different family, one that was far harder to study and far stranger in how it moved through the universe. Everything you can touch is made of quarks. The chair under you, the air in your lungs, the screen you might be looking at right now. Every proton and neutron in every atom in every object in the observable universe is built from quarks, bound together by a force so strong it has never been directly observed in isolation. You cannot pull a quark out of a proton and hold it by itself. The moment you try, the energy you use creates new quarks to replace the one you pulled. They always come in groups. There are 6 flavors. Up and down are the everyday ones. A proton holds 2 up quarks and 1 down quark. A neutron holds 2 down quarks and 1 up quark. The other 4 flavors, strange, charm, bottom, and top, are heavier and unstable. They do not last long in normal conditions. They only appear briefly when particles collide at high energies, like inside the accelerators physicists use to probe the rules of nature. What makes quarks central to the matter-antimatter mystery is how they interact with the weak nuclear force. The weak force governs certain types of particle decay, the process where an unstable particle breaks apart into lighter ones. And during those decay processes, quarks can change flavor. A strange quark can flip into an up quark. A bottom quark can flip into a charm quark. These transitions happen at specific rates, following precise rules. CP symmetry required that these transitions happen at identical rates for quarks and for antiquarks. A quark changing from one flavor to another should happen at the same rate as the equivalent antiquark undergoing the equivalent change, just mirrored. If the rates differ, the symmetry is broken. When scientists measured particles containing heavier quarks, they found the rates did differ. Particles built from bottom quarks showed clear CP violation. The matter version and the antimatter version of these particles decayed at different speeds and into different combinations of products. The violation was larger than in kaons, measurable, confirmed by multiple experiments at different facilities across different decades, and still not enough. Even combining every confirmed source of CP violation in all known quark interactions, the total predicted asymmetry falls short of what the universe actually contains by many orders of magnitude. The quark contribution is real and measurable, but it is a drop compared to the ocean of asymmetry required to explain our existence. This is the core frustration of the baryon asymmetry problem. Scientists have confirmed that CP violation exists. They have measured it in multiple particle types. They have a theoretical framework, the Standard Model, that explains why it arises from quark mixing. And that framework, as successful as it is at describing everything physicists can currently test, produces a universe that should be nearly empty. The Standard Model is one of the most tested theories in science. It describes the behavior of all known particles and forces with extraordinary accuracy, and it is provably incomplete because the universe it predicts should not contain enough matter to build a single star. Something is missing. Some mechanism, some particle, some force or symmetry violation not yet discovered must be responsible for the extra asymmetry. Physicists have been chasing it for decades, and in recent years, two very different types of experiments have found the most promising leads yet. One involves a machine the size of a city. The other involves a particle so ghostly it passes through the entire Earth as if it were not there. Physics has a rulebook. Scientists call it the Standard Model. It is a framework built over about 50 years of experiments and theoretical work that describes every known particle and every known force except gravity. It tells you how quarks bind into protons, how electrons orbit atoms, how light interacts with matter, how radioactive decay works, how particles acquire mass, all of it in one mathematical framework. The Standard Model has passed every test scientists have thrown at it. Predictions made using its equations have been confirmed by experiments thousands of times. It predicted the existence of particles before they were discovered, and when those particles were searched for, they were found exactly where the math said they would be. The Higgs boson, the particle responsible for giving other particles their mass, was predicted by the Standard Model decades before the Large Hadron Collider confirmed it in 2012. By any measure, the Standard Model is one of the most successful scientific theories ever constructed. It is also known to be incomplete. Gravity is missing from it. Dark matter, the invisible substance that makes up about 27% of the universe, has no particle in the Standard Model to explain it. Dark energy, the force driving the accelerating expansion of the universe, is not in the model either. And most relevant to this story, the matter-antimatter asymmetry of the universe cannot be explained by the Standard Model alone. Scientists know this. The people who built the model know this. The CP violation that the Standard Model permits, coming from quark interactions, is real and measured. It is also thousands of times too small to account for the matter we observe. The rulebook describes the rules correctly, But the rules it describes are not enough to build the universe we live in. This means either the model is missing something, a new particle or a new interaction not yet discovered, or the explanation lies in extreme conditions that only existed in the first fractions of a second after the Big Bang. Conditions that particle colliders cannot fully recreate. Both possibilities have driven experimental physics for the last several decades. The hunt takes two main forms. First, build accelerators powerful enough to create conditions at the edge of what the standard model describes, and look for deviations. A result that does not match the prediction is a crack. A crack means something new is there. Second, study particles that the standard model predicts behave nearly symmetrically, and look for violations larger than the model allows. Any excess violation points to physics beyond the current framework. The second approach turned out to be especially productive with a family of particles called baryons. Baryons, like protons and neutrons, are made from three quarks. For decades, scientists focused CP violation studies on lighter, easier to produce particles. Baryons were harder to study in large quantities. Then, the Large Hadron Collider changed that. At the world's most powerful particle accelerator, buried in a circular tunnel 17 miles around beneath the French and Swiss border, scientists began producing baryons by the tens of thousands, watching them decay, measuring the rates, comparing matter to antimatter. And in 2025, they found something that made the entire field stop and pay attention. What they found inside those baryon decays was the kind of result that gets physicists out of bed in the middle of the night to double-check the data. It sits 60 to 300 feet underground, straddling the border between France and Switzerland. The tunnel is 17 miles in a nearly perfect circle, wide enough to drive a car through, lined with supercooled magnets, each one chilled to temperatures colder than outer space, using liquid helium to reach about negative 456 degrees Fahrenheit. Those magnets create the most intense magnetic fields on Earth, guiding beams of protons around the ring at speeds approaching the speed of light. The Large Hadron Collider at CERN is the most complex machine ever built by human beings. It took decades to design, billions of dollars to construct, and the combined effort of thousands of engineers, physicists and technicians from over 100 countries. The accelerator takes protons, strips away their electrons, and injects them into the ring. Two beams travel in opposite directions. Then, at 4 specific collision points around the ring, the beams cross. Protons smash into protons at energies so high that the collision briefly recreates conditions similar to the first fractions of a second after the Big Bang. When protons collide at those energies, they do not simply bounce, they shatter. The collision produces a spray of particles, some of them exotic types that do not exist anywhere in the ordinary universe at ordinary temperatures. These exotic particles appear for fractions of a second, decay into lighter particles, and leave tracks in surrounding detectors. Those detectors are the size of apartment buildings, built in underground caverns around the collision points. One of those detectors, called the LHCb experiment, is specifically designed to study the difference between matter and antimatter. It captures the products of particle decays with extraordinary precision and measures whether matter particles and antimatter particles behave identically. Every deviation from perfect symmetry is a signal. Every signal is a clue. The collider has been running in various forms since 2008. It discovered the Higgs boson in 2012. Since then, it has produced a steady stream of precision measurements, refining the parameters of the standard model and searching for deviations that point beyond it. The sheer scale of what the machine produces is almost impossible to grasp. In a single second of operation, the beams can generate hundreds of millions of particle collisions. The detectors record every significant event. The data stream is so large that even with sophisticated filtering to discard uninteresting collisions, it fills computer storage at a rate that would exhaust a home computer's hard drive in seconds. Scientists from around the world analyze that data. Teams sift through hundreds of millions of recorded decays, looking for specific particles, specific decay patterns, specific deviations from the standard model. The analysis of a single major result can take years of work by hundreds of physicists before it reaches publication. And in 2025, one of those results landed. A team at the LHCb experiment had been studying a type of baryon called the lambda B. A baryon made of 3 quarks, one of which is the heavy bottom quark. They had collected data on over 80,000 of these particles and their antimatter equivalents. They measured how each version decayed. The result showed something that had never been seen before in this family of particles. And what it means for the matter-antimatter mystery is something physicists are still working through. In 2025, scientists at CERN published a result that the physics community had been waiting for since 1964. For the first time in history, researchers observed a clear difference in how baryons and their antimatter versions behaved. The lambda B baryon, built from 3 quarks, including 1 bottom quark, decayed into specific lighter particles at a measurably different rate than its antimatter counterpart did. Matter and antimatter baryons, given the same conditions, chose different paths. The difference was 5%. The lambda B baryon decayed into 1 specific combination of particles, 5% more frequently than the anti-lambda B decayed into the equivalent combination. 5% sounds small. In the world of particle physics, it is enormous. And in baryons, the family of particles that makes up all atomic matter in the universe, it had never been confirmed before. The team had analysed over 80,000 individual decays. That number is important. Single events mean nothing in particle physics. Flukes happen. Statistical noise mimics real signals all the time. Over 80,000 measured decays, running through sophisticated analysis, is the kind of dataset that makes a result trustworthy. The statistical confidence of the finding was high enough to declare it a genuine discovery. The measurement was a direct observation of CP violation in baryons, not in kaons, not in particles built from 1 quark and 1 antiquark, but in baryons, in the exact family of particles that composes protons and neutrons, in the particles that make up you. Scientists had predicted that baryons should show CP violation based on the theoretical framework of quark mixing. But predicting something and measuring it are entirely different achievements. The measurement confirmed that the asymmetry between matter and antimatter extends into the most fundamental building blocks of visible matter. To understand why this matters beyond the headlines, you have to understand what baryons are and why finding an imbalance specifically in them is significant. The previous CP violation results, in kaons and in particles called B mesons, involved particles built from 1 quark and 1 antiquark. Those particles are not the same as the matter you are made of. They are exotic, short-lived, and do not form the stable structures of atoms. Baryons are different. They are the particles at the foundation of all atomic nuclei. Every atom in the observable universe has a nucleus built from baryons. Finding that matter, baryons and antimatter baryons do not behave identically is a direct measurement of the asymmetry operating at the most basic level of physical reality. The result does not solve the mystery by itself. The 5% difference measured in lambda B decays, while significant, is still too small on its own to account for the total asymmetry of the universe. The full explanation requires a violation that operated at an enormous scale in the very early universe, under conditions far more extreme than anything the Large Hadron Collider can recreate. But the discovery proves that CP violation runs deeper into matter than any previous experiment confirmed. It opens new pathways for calculation, new predictions to test, and new questions about whether even larger violations might be hiding in other baryon types not yet studied. The search, already decades old, now has a new confirmed foothold. And meanwhile, a completely different experiment on the other side of the planet was finding something that might dwarf even this. Most particles studied in CP violation experiments are exotic, temporary, built in colliders and gone in a fraction of a second. Baryons are different. A baryon is any particle made of 3 quarks bound tightly together by the strong nuclear force. Protons are baryons, neutrons are baryons. They are not exotic or temporary. They are the foundation. Every atomic nucleus that has ever existed, in every star that has ever burned, in every planet that has ever formed, is made from baryons. When scientists say they want to understand why matter survived the Big Bang, they are asking a question specifically about baryons. The surviving particles that built the universe were baryons. The imbalance between matter and antimatter that allowed existence is called the baryon asymmetry problem, because baryons are the particles at the heart of it. So when the LHCb experiment found CP violation directly in baryons in 2025, it was not just another entry in the long list of CP violation measurements, it was a measurement of the asymmetry in the exact particle type that the asymmetry problem is about. Previous measurements of CP violation in kaons and B mesons were valuable because they confirmed the principle. They showed that nature breaks the matter-antimatter symmetry. But kaons and B mesons are not the matter the universe kept. They are not what stars are made of. They are not in your bones. Finding CP violation in them proved the phenomenon was real, but left open the question of whether baryons, specifically, showed the same behavior. The answer, as of 2025, is yes. Baryons show CP violation. The 5% difference in lambda B decay rates is a confirmed signal, not a statistical fluke, not an artifact of the detector, but a genuine physical measurement of nature, treating matter baryons and antimatter baryons differently. This has a practical implication for theory. Different types of CP violation have different underlying causes in the mathematics of particle physics. Measuring the violation in baryons tells theorists something specific about which processes are responsible. It constrains their models, it rules out some explanations and makes others more plausible. The data from 2025 is now being used to refine calculations about what the very early universe looked like, and which mechanisms could have produced the asymmetry at scale. There is also a deeper implication. If baryons show CP violation, and if that violation is connected to the physics of the early universe, then the lambda B baryon result is a window, a small, carefully measured window into the mechanism that decided, in the first fractions of a second after the Big Bang, whether the universe would exist or empty itself out. The window is open. The view through it is not yet complete. The level of violation measured at the Large Hadron Collider is still too small to account for everything. The gap between the known violations and the required asymmetry remains large, which means the majority of the answer is still missing. And the most promising place physicists are currently looking for it involves particles so elusive they were considered unmeasurable just a few decades ago. Particles that travel through solid rock as easily as light travels through air. Particles that pass through your body by the trillions every second. And you feel absolutely nothing. Right now, trillions of particles are passing through your body. Every second. Through your skin, through your organs, through the atoms that make up every cell. They do not bounce off anything. They do not ionize anything. They do not trigger any sensation in any nerve. They pass through you the way light passes through glass, except glass actually slows light down. These particles barely notice you are there. They are called neutrinos. And they may hold the answer to the biggest mystery in physics. Neutrinos are produced in enormous quantities by nuclear reactions. The sun produces them in vast floods during the fusion reactions that power it. Every second, about 65 billion neutrinos from the sun pass through every square inch of your body facing the sun. At night, they pass through the entire Earth first, then through you. The planet offers essentially no resistance. To a neutrino, the Earth is nearly as transparent as empty space. Nuclear explosions produce neutrinos. Certain types of radioactive decay produce them. When massive stars collapse into supernovas, they release more energy in a 10-second burst of neutrinos than the sun will emit in its entire lifetime. Neutrinos flood outward in every direction and travel across the galaxy, passing through everything in their path. They interact with regular matter so rarely that to stop just one of them, you would need a wall of lead about 1 light-year thick. 1 light-year. The distance light travels in an entire year. That is how weakly neutrinos interact with anything. Despite this, physicists catch them. Underground laboratories, built deep beneath the mountain ranges and beneath the ocean floor, use tanks of extremely pure water or special materials as targets. Occasionally, very rarely, a neutrino passing through the tank will interact with an atom and produce a tiny flash of light. Sensitive detectors surrounding the tank record the flash. From millions of these rare catches, scientists build up a picture of neutrino behavior. There are 3 types of neutrinos. Scientists call them flavors, electron neutrinos, muon neutrinos, and tau neutrinos. And they do something genuinely strange as they travel. They change flavor. A neutrino that starts as an electron neutrino can arrive somewhere as a muon neutrino. It oscillates between flavors over distance, following a quantum mechanical pattern that depends on its energy and the distance it has traveled. This flavor changing was confirmed experimentally in the late 1990s, winning a Nobel Prize. It also proved that neutrinos have mass, however tiny, because massless particles cannot oscillate in this way. The Standard Model originally predicted neutrinos were massless. The oscillation result proved the Standard Model wrong on this point. And here is where the matter-antimatter mystery enters. Scientists began asking whether neutrinos and antineutrinos oscillate in exactly the same way. If the symmetry is perfect, an antineutrino should change flavors at the same rate and in the same pattern as a neutrino. If the symmetry is broken, the rates will differ. A broken symmetry in neutrinos would be CP violation in an entirely new family of particles, one with a potential connection to the early universe that dwarfs anything found in quarks. The experiment designed to catch this difference was built in Japan, and what it found in 2020 is the reason neutrinos are now the most watched particles in physics. Japan sits on a collision zone between tectonic plates. The ground shakes regularly. The mountains are steep. The geology is complex. And somewhere beneath those mountains, a beam of neutrinos travels in a straight line through 295 kilometers of solid rock, fired from one end of the country toward a detector buried deep underground at the other end. The experiment is called T2K, Tokai to Kamioka, the names of the 2 locations involved. Tokai is a small city on the Pacific coast, home to a facility that generates an intense beam of muon neutrinos using a proton accelerator. Kamioka is a mine in the mountains of the Gifu Prefecture, about 183 miles away as a straight line through the earth. Inside that mine, buried under half a mile of rock, sits a detector called Super Kamiokande, a cylindrical tank holding 50,000 tons of ultra-pure water, lined wall to wall with thousands of sensitive light detectors. The beam leaves Tokai. It travels through the crust of the earth, as if the rock were not there. After 183 miles, A tiny fraction of the neutrinos interact with the water in Super Kamiokande and produce a faint flash of light. The detectors catch the flash. Scientists record the event. Over years of operation, those rare catches accumulate into meaningful data. But here is what makes T2K different from simply counting neutrinos. The experiment alternates. For part of its run, it fires a beam of muon neutrinos. For another part, it fires a beam of muon antineutrinos. The same distance, the same detector, the same measurement. The only difference is matter versus antimatter. If CP symmetry holds perfectly in neutrinos, the two beams should oscillate at the same rate. The same fraction of muon neutrinos should transform into electron neutrinos over that 183-mile journey. And the same fraction of muon antineutrinos should transform into electron antineutrinos. If the rates differ, the symmetry is broken. CP violation in neutrinos. A completely new and potentially enormous source of asymmetry between matter and antimatter. The experiment requires extraordinary patience. Neutrinos interact so rarely that even with a powerful beam and a 50,000-ton detector, meaningful statistics take years to accumulate. The scientists running T2K do not measure results in days or weeks. They count events one by one over years of continuous operation, waiting for the data to become strong enough to say something definitive. The setup also requires extraordinary engineering precision. The beam must be aimed with extreme accuracy across 183 miles of Earth's curvature. The detector must capture and correctly identify the rare neutrino interactions. Background events, other particles that trigger the detector and mimic neutrino signals, must be carefully filtered out. And in 2020, after years of running, the T2K collaboration published their analysis. They compared the oscillation rates of the two beams. They measured how many muon neutrinos had transformed into electron neutrinos versus how many muon antineutrinos had transformed into electron antineutrinos. The rates were different, significantly different. The neutrinos oscillated far more readily than the antineutrinos. The data showed a strong preference for matter over antimatter in the neutrino family, a hint of CP violation larger than anything found in quarks. The results sent a wave through the physics community. Because if neutrinos violate CP symmetry at this scale, the implications reach all the way back to the Big Bang itself. The kaon discovery was significant. The baryon discovery was significant. The neutrino result could be something else entirely. Here is why. The CP violation found in quarks is real, measured, and confirmed by multiple experiments. But when scientists run the calculations, the total amount of asymmetry that quark CP violation can generate in the early universe falls far short of explaining what we observe. The gap is enormous. Quarks produce matter and antimatter at nearly identical rates. The observed universe requires that matter and antimatter were produced at very different rates. Neutrinos, if they violate CP symmetry, could fill that gap. The reason comes down to a theory called leptogenesis. Leptons are a family of particles that includes electrons and neutrinos. Leptogenesis is the idea that in the very early universe, extremely heavy versions of neutrinos, far heavier than any neutrino detected today, existed briefly and then decayed. And if they decayed in a way that violated CP symmetry, they could have produced more leptons than antileptons. That lopsided decay would have left an excess of regular matter particles in the lepton family. Then, a process the early universe allowed would have converted some of that lepton excess into a baryon excess, producing more baryons than antibaryons. The extra baryons survived the annihilation. The universe got its matter. This is the theoretical chain. Heavy neutrino decays unevenly. Lepton excess forms. Lepton excess converts to baryon excess. Baryon excess survives annihilation. Stars, planets, U. The chain only works if neutrinos genuinely violate CP symmetry. The T2K result in 2020 showed strong hints that they do. The oscillation rate difference between neutrinos and antineutrinos pointed toward a large CP violation in the neutrino family. Strong hints are not the same as proof. In physics, strong hints are exciting and publishable and important, but declaring something a confirmed law of nature requires a higher standard of statistical certainty. The T2K data in 2020 showed a preference in the data consistent with large CP violation, but the statistical strength was not yet enough to rule out the possibility of a random fluctuation mimicking the signal. The physics community responded by building bigger. Super Kamiokande is already a 50,000-ton detector. Its successor, Hyper Kamiokande, is a detector 10 times larger. Still under the same Kamioka Mountains, still watching for the same neutrino signals. But with 10 times the volume of ultra-pure water, it captures neutrino events 10 times more frequently. These statistics that took years to build at Super Kamiokande will accumulate in months at Hyper Kamiokande. Hyper Kamiokande is designed to answer the neutrino CP violation question definitively. Either the hint is real and becomes confirmed, or the larger dataset shows the 2020 result was a statistical fluctuation, and the truth is different. Either outcome advances science. One of them might close the biggest open question in physics. There is also a parallel experiment in the United States called DUNE. A beam fired from Fermilab near Chicago will travel 800 miles through the Earth to a detector in South Dakota. A different distance, a different baseline, a different energy range, the same question. Two independent experiments from opposite directions closing in on the same answer. What both experiments are chasing is the moment the data becomes undeniable. The moment the signal is clear enough that no statistical objection can stand. And if that signal confirms what T2K hinted at, then leptogenesis moves from a compelling theory to the leading explanation of our existence. But there is something even stranger hiding one level deeper, in the heaviest version of the neutrino that physics has ever imagined. Neutrinos do something no other particle does. They change identity mid-flight. A neutrino born as one type arrives somewhere else as a different type entirely. A muon neutrino leaves a nuclear reaction, travels through hundreds of miles of rock, and arrives at a detector transformed into an electron neutrino. The particle changed what it is during the journey. It oscillated between identities, governed by quantum mechanics, following a pattern that depends on its speed and the distance it traveled. This is not a metaphor. The neutrino does not slowly transition from one flavor to another. Quantum mechanically, it exists in a superposition of all three flavors simultaneously as it travels, and when it interacts with a detector, the measurement collapses that superposition into one specific identity. The probability of which flavor it collapses into depends on how far it has traveled. Imagine a coin spinning in the air. While it spins, it is neither heads nor tails. Both outcomes are possible simultaneously. When it lands, the spin ends and one outcome becomes real. A neutrino traveling through space is the spinning coin. Its flavor is undetermined until it interacts with something. The oscillation pattern has a specific mathematical shape, determined by the differences in mass between the three neutrino types and by a set of mixing angles, numbers that describe how strongly each flavor mixes with the others. Experiments measure these angles by watching how neutrino beams change composition over distance. One of those mixing angles, the one physicists label delta CP, is the key to the matter-antimatter question. If delta CP is 0, neutrinos and antineutrinos oscillate identically. Symmetry holds. If delta CP is any other value, the oscillation rates differ. CP violation exists in the neutrino sector. T2K in Japan measured delta CP in 2020. The result pointed strongly toward a value that would produce maximum violation. The antineutrinos were oscillating significantly less than the neutrinos over the same distance. The symmetry was broken, and potentially broken by a large amount. The specific value the data pointed toward is one that theorists find exciting because it maximizes the lopsidedness between matter and antimatter neutrino behavior. If delta CP is near that maximum value and confirmed by future experiments, the leptogenesis mechanism gains enormous explanatory power. The math works out to produce the right amount of asymmetry to explain our universe. Every mixing angle and every oscillation rate that gets measured constrains the theory further. The experimental program in Japan and the upcoming program in the United States are essentially a coordinated global effort to measure delta CP precisely enough to know whether it is the key. Meanwhile, the oscillation result itself, confirmed across multiple experiments now, already had profound consequences for physics. It proved neutrinos have mass. Small mass, but real. This single fact broke the standard model and opened the door to extensions of physics that include the heavy neutrino ancestors of today's light ones, the ones leptogenesis requires. The fact that today's neutrinos are so light raises its own question. Why so light? Other particles with mass are far heavier. What mechanism drives neutrino mass down to almost nothing? The answer physicists favor involves the heavy ancient neutrinos directly. A mathematical seesaw where one end holds the heavy ancient neutrino and the other holds the light modern one. The heavier one goes up, the lighter one comes down. The mechanism is called the seesaw mechanism, and it naturally produces both the ghostly lightness of modern neutrinos and the existence of the heavy ancestors that leptogenesis requires. The seesaw sits at the intersection of everything: light neutrinos, heavy ancestors, leptogenesis, CP violation, the origin of matter, all connected by one mathematical framework. And what comes next stretches that framework into territory that borders on the genuinely mind-bending. The universe made a choice in the first fraction of a second. Under conditions so extreme that no physics experiment has ever come close to recreating them, a particle decayed. A heavy particle, far more massive than anything in the modern zoo of particles, broke apart into lighter ones. And when it broke apart, it did not break evenly. It left behind slightly more leptons than antileptons. That choice, made trillions of times across every corner of the young universe, added up to the only thing that mattered. A lopsided result, baked into the fabric of reality before a single atom had formed. This is leptogenesis. Lepto from lepton, the family of particles that includes electrons and neutrinos. Genesis from the Greek word for origin. Leptogenesis is the theory that the origin of the matter-antimatter imbalance lies in the lepton family, in heavy ancient neutrinos that no longer exist in the cold universe of today. The theory was proposed in 1986 by two physicists, Motohiko Yoshimura and later formalized by Masataka Fukugita, and Tsutomu Yanagida. The mathematics is elegant. The heavy neutrinos, called right-handed neutrinos because of a quantum property called spin, were extremely massive. They existed only briefly in the hot early universe. As the universe cooled, they could no longer be created. The ones already present began decaying. The decay was the critical moment. A heavy neutrino could decay into a lepton plus other particles. Its antimatter version, the heavy antineutrino, could decay into an antilepton. If CP symmetry held perfectly, both decays happened at identical rates, equal leptons and antileptons. The imbalance would be zero. If CP symmetry was broken in these decays, the heavy neutrino decayed into leptons slightly more often than the heavy antineutrino decayed into antileptons. A tiny excess of leptons built up, not by much, but consistently. In every corner of the universe, in every decay of every heavy neutrino, the same small preference played out the same way. Then, a process the hot early universe allowed converted that lepton excess into a baryon excess. The mechanism behind this conversion involves a quirk of the Standard Model that operates only at extremely high temperatures, called Sphaleron processes. Sphalerons are not particles. They are configurations of energy fields that temporarily connect the lepton and baryon numbers of the universe, allowing one to influence the other. As the universe cooled past a certain temperature, sphalerons froze out and stopped operating. Whatever imbalance existed at that moment became locked in. The frozen-in baryon excess was the 1 in a billion, the survivors. Leptogenesis is compelling because it ties together 3 separate puzzles. It explains the smallness of neutrino mass through the seesaw mechanism. It explains the matter-antimatter imbalance through CP violation in heavy neutrino decays, and it links both of these to the thermal history of the early universe in a mathematically consistent framework. The problem is that the heavy neutrinos required for leptogenesis are far too massive to produce in any particle accelerator that currently exists or is currently planned. They are almost certainly beyond the reach of direct experimental detection. Scientists cannot build a collider big enough to make one, so the evidence for leptogenesis must be indirect. It comes from measuring CP violation in the light neutrinos that are the descendants of the heavy ones. If light neutrinos violate CP symmetry strongly, it points to a family of particles where large violations are possible, which supports the idea that the heavy ancestors violated it at the scale required. The T2K hint is one piece of that indirect evidence. The upcoming measurements are more, and separately, one of the most surprising facts about the matter-antimatter mystery is hiding in something far more familiar than underground tunnels. The paper landed in April 2020. The T2K collaboration, hundreds of physicists across dozens of institutions in Japan, the United Kingdom, the United States, Canada, and several other countries, published their latest measurement of neutrino oscillations. It had been 7 years since T2K began producing publishable results. Years of patient data collection, one neutrino at a time, one flash of light at a time, in a tank buried under half a mile of rock in the mountains of Japan. The result was the strongest experimental hint yet that neutrinos and antineutrinos oscillate at different rates. The team had measured 2 things: how many muon neutrinos transformed into electron neutrinos over the 183-mile journey from Tokai to Kamioka, and how many muon antineutrinos transformed into electron antineutrinos over the same journey. If CP symmetry holds, both fractions should be equal. The data showed a striking asymmetry. 90 muon neutrinos had transformed into electron neutrinos. 15 muon antineutrinos had transformed into electron antineutrinos. The ratio of transformation was far higher for the matter neutrinos than for the antimatter neutrinos. The difference was large. Statistically, the result pointed strongly toward a large violation of CP symmetry. The value of delta CP, the mixing angle that controls this asymmetry, was measured to be near the maximum possible violation. The measurement excluded the scenario of zero CP violation, meaning perfect symmetry between neutrinos and antineutrinos at a confidence level of about 95%. In particle physics, 95% confidence is significant but not sufficient to declare a discovery. The field requires what scientists call 5 sigma confidence, meaning the probability that the result is a random statistical fluctuation is less than 1 in 3.5 million. The 2020 T2K result was roughly at the 2 sigma level, strong enough to be a serious hint, not strong enough to be a confirmed discovery. That distinction matters enormously. The history of particle physics is full of 2 sigma and 3 sigma hints that vanished when more data came in. False signals that looked real until the statistics caught up. The physics community responded to the T2K result with excitement and caution in equal measure. The excitement came from the size of the signal. A 2 sigma hint pointing toward maximum CP violation is not a casual observation. The data was pointing in a specific direction, and that direction was the one leptogenesis needed it to point. The caution came from hard experience. Many hints evaporate. Data can be misunderstood. Systematic errors in complex experiments are hard to eliminate completely. The only way to know whether the signal was real was to collect more data. The T2K collaboration continued running the experiment. More data arrived. The signal persisted. The confidence level crept upward. Meanwhile, the physics community began designing the instruments that would finally settle the question with enough statistical certainty to cross the discovery threshold. The scale of effort required to turn a hint into a law of nature is staggering. Thousands of scientists, billions of dollars, decades of construction and operation, all to measure the behavior of particles that pass through solid rock without leaving a trace. And while that effort was building, a separate discovery in a completely unexpected place was reshaping how scientists think about where antimatter hides today. 95% sounds like certainty. In daily life, 95% confidence that something is true would end almost any argument. But particle physics does not operate by everyday standards. The field has been burned before by results that looked iron solid at 95%, and later dissolved when more data arrived. Extraordinary claims about the fundamental nature of reality demand extraordinary evidence. The standard threshold is 5 sigma, 5 standard deviations from the null result, meaning the probability that the measured signal is a random fluctuation is less than 1 in 3.5 million. That sounds excessive. It is also necessary. Thousands of analyses are run on particle physics data every year. If the threshold were lower, false discoveries would appear regularly just by chance. The 5 sigma rule keeps the record clean. The T2K result in 2020 sat at approximately 2 sigma. Strong, suggestive, scientifically important, and firmly in the category of hint rather than discovery. The gap between 2 sigma and 5 sigma represents an enormous amount of additional data. To cross from 95% confidence to 1 in 3 million confidence, T2K needed far more neutrino interactions recorded in the detector, more beam time, more years of operation, or a much larger detector. The situation is compounded by systematic uncertainties. Systematic errors are not statistical flukes. They are potential biases in the experimental setup itself. The beam might not produce neutrinos and antineutrinos in exactly the proportions the model assumes. The detector might respond slightly differently to electron-neutrino interactions versus electron-antineutrino interactions. The nuclear interactions of neutrinos inside the water molecules of the detector introduce complicated physics that must be modeled carefully. Each of these sources of uncertainty is controlled and estimated by the experimental team, but none can be reduced to zero. As the statistical precision of the measurement improves with more data, the systematic uncertainties become more important. At some point, the measurement becomes systematics limited rather than statistics limited, meaning collecting more data no longer helps, because the dominant uncertainty is not in the number of events, but in the understanding of the detector. Hyper-Kamiokande addresses both problems simultaneously. The larger detector produces more events per unit time, improving statistics faster. The detector design also includes improvements that reduce systematic uncertainties compared to Super Kamiokande. The combination is designed to reach the 5 sigma threshold within roughly a decade of operation. DUNE in the United States provides an independent measurement. If both DUNE and Hyper Kamiokande find consistent results pointing toward large CP violation in neutrinos, the combined weight of two independent experiments with different designs, different baselines, and different systematic uncertainties becomes overwhelming. Even the most skeptical physicist would accept a 5 sigma result from two independent experiments pointing the same direction. The community is not waiting passively. While Hyper Kamiokande and Dune build toward their definitive measurements, theoretical physicists are working to understand what each new piece of data implies for leptogenesis models. Every new measurement constrains the allowed range of parameters. Every hint that holds up narrows the field of possible explanations. The process is slow by any standard outside of science. It is also extraordinarily rigorous, and the answer, when it arrives with 5 sigma certainty, will either confirm leptogenesis as the mechanism behind our existence, or shatter the current theoretical framework completely, pointing towards something no physicist has yet imagined. Both outcomes would be transformative. Both are possible. The experiment has not finished speaking. The most dramatic particle in physics sits inside a medical scanner. Positron emission tomography, the scanning technology used in hospitals around the world to image tumors, map brain activity, and diagnose disease, runs on antimatter. Specifically, it runs on positrons, the antimatter counterpart of the electron, and it uses them by the billions, every day, in clinics and hospitals across every continent. The positron was predicted mathematically by Paul Dirac in 1928, before it had ever been observed. Dirac was solving equations that combined quantum mechanics with Einstein's theory of special relativity, and the math kept producing a solution with a negative energy state for the electron. He initially tried to explain it away. Eventually he accepted what the equation was telling him. There should be an electron with positive charge. An antimatter electron. Carl Anderson confirmed it 4 years later in 1932. He was studying cosmic rays passing through a cloud chamber, and he found a particle with the same mass as an electron but curving the wrong way in a magnetic field. A positive electron. A positron. The first antimatter particle ever directly observed. The Nobel Prize in Physics went to both men, and a technology built on their discovery now scans millions of human bodies every year. Here is how it works. A radioactive substance, specifically chosen to emit positrons during its decay, is injected into a patient's body. The substance is chemically similar to glucose, so cells that consume large amounts of energy, including cancer cells and active brain regions, absorb it quickly. As it decays, it emits positrons inside the patient's tissue. Each positron travels a tiny distance, about 1 millimeter, before it encounters an electron in the surrounding tissue. The two particles annihilate each other completely. The annihilation produces 2 photons of energy fired in exactly opposite directions at the speed of light. Detectors arranged in a ring around the patient catch both photons simultaneously. Because the photons always travel in opposite directions, the detectors can calculate precisely where the annihilation happened. A computer assembles thousands of these paired detections into a 3-dimensional map of where the radioactive substance concentrated inside the body. Tumors light up, active brain regions glow, diseased tissue becomes visible with a precision that other imaging methods cannot match. The antimatter particle that physicists spent decades trying to explain, the one produced in the Big Bang in equal amounts to matter before it was supposed to destroy everything, is now a routine clinical tool. A life-saving diagnostic technology built on the most fundamental physics in the universe. This is one of the places where the deep abstraction of particle physics connects directly to the everyday world. The matter-antimatter asymmetry problem sounds remote. The Kaon experiment, the LHCb baryon result, the neutrino beam fired through a mountain, these feel like the concerns of specialists in underground laboratories. But positrons are in the hospital down the street, Antimatter is not exotic, it is medical. The positrons in those scanners are not produced in particle accelerators. They are produced by specific radioactive isotopes, manufactured in small medical cyclotrons at hospitals and dedicated facilities. The isotopes have short half-lives, measured in minutes, so they must be made close to where they're used. A small cyclotron, about the size of a large car, produces the radioactive material. Technicians rush it to the scanner. The scan happens, the antimatter annihilates, and the image appears. Antimatter, the thing that should have been equal to matter at the Big Bang, the thing that should have erased everything, is now erasing cancer cells. The sky above you is full of antimatter, not hypothetically, not as a theoretical prediction. Cosmic rays, high-energy particles fired outward by supernovas, neutron stars, and the violent regions around supermassive black holes across the galaxy stream through space in every direction. When these cosmic rays slam into the upper atmosphere of Earth, roughly 15 miles above your head, they collide with air molecules and produce showers of secondary particles. Some of those particles are positrons, antimatter electrons, created in the atmosphere and raining downward toward the ground. They do not reach you. The atmosphere absorbs them before they travel far. Each positron produced in an atmospheric collision quickly meets an electron, and the pair annihilates, producing two photons that continue downward as ordinary light. By the time you're hit with any radiation from cosmic ray showers, the antimatter component has already erased itself in the upper atmosphere. But the signal of that annihilation is measurable. Space-based instruments detect the burst of photons produced when atmospheric positrons meet electrons. The AMS-02 experiment, a particle detector mounted on the International Space Station, has been recording cosmic ray particles since 2011. It has detected hundreds of thousands of positrons arriving from space directly before they even enter the atmosphere. These positrons come from the galaxy itself, produced in energetic events far from Earth and traveling across interstellar space to reach us. Scientists use this cosmic antimatter rain as a tool. By measuring the energy distribution of incoming positrons and comparing it to what known astrophysical processes should produce, they search for unexpected excesses. An unexpected surplus of high-energy positrons could signal a new source, possibly the annihilation of dark matter particles somewhere in the galaxy. The AMS-02 data has found some puzzling excesses that researchers are still working to explain. Meanwhile, there is a more personal connection. Some of the potassium in your body is radioactive. Potassium-40, a naturally occurring isotope present in every banana, every piece of bread, every glass of milk, decays by emitting a positron. Your body contains enough potassium-40 to produce roughly 5,000 positron emissions per hour from your own tissues. Each one annihilates almost instantly with a nearby electron, releasing two photons that travel through your body and out into the room around you. You are a very faint source of antimatter radiation. So is every living thing. The banana sitting on a counter nearby is genuinely, measurably producing antimatter. This natural radioactivity is completely harmless. The positrons produced by potassium-40 annihilate so close to their origin that the energy is absorbed by tissue at negligible levels. You have been living in the same body with radioactive potassium your entire life. Every cell that contains potassium, which is most of them, has been hosting this process since before you were born. The Big Bang produced antimatter in such overwhelming quantities that it nearly erased the universe. And today, antimatter still falls from the sky, still emerges from hospital scanners, and still appears spontaneously inside the living tissue of every human body. It never stopped being part of reality. It just became too rare to cause anything but the most precisely controlled and beneficial interactions. The scale dropped from cosmic to microscopic. But the same particles, the same annihilation, the same physics that defined the first second of the universe continues playing out all around you at every moment. Antimatter is the most expensive substance ever produced by human beings. Not expensive in the way gold or platinum is expensive. Those can be mined and refined in large quantities. Antimatter cannot be mined anywhere. It has to be manufactured, particle by particle, using particle accelerators that consume enormous amounts of electricity and produce vanishingly small yields. At CERN, the process of making antihydrogen, the simplest antiatom, requires producing antiprotons in the accelerator, slowing them down to almost zero velocity, capturing them in a magnetic trap, combining them with positrons to form whole antiatoms, and holding all of it in a carefully maintained vacuum so the antihydrogen never touches the walls of the container. If it touches the walls, both the antihydrogen and a tiny portion of the wall material annihilate instantly. The energy released is tiny. The antimatter quantity is so small that the explosion would not warm a cup of water. But the antimatter is gone, and producing more requires starting the entire process again. The magnetic trap works by using powerful superconducting magnets to create a field that pushes the antiatoms away from the walls and holds them suspended in the center of a vacuum chamber. No material can contain antimatter directly. It must float inside an invisible magnetic cage, never touching anything physical. The ALPHA experiment at CERN has successfully trapped antihydrogen atoms and held them long enough to study their properties. The goal is to compare hydrogen and antihydrogen directly. If the two are perfectly identical in their spectroscopic signatures, the frequencies of light they absorb and emit, then CP symmetry holds at least in atomic hydrogen. If there is a measurable difference, it is a signal pointing toward new physics. So far, the comparisons show hydrogen and antihydrogen behaving identically within the precision of the measurements. The symmetry holds at the atomic level, at least as well as current instruments can detect. Improving the precision of these measurements is an ongoing program, because any tiny deviation would be enormous news. The cost of producing antihydrogen is genuinely staggering. Estimates place the cost of producing a single gram of antimatter, if it were even physically possible to produce that quantity, at roughly $62 trillion using current technology. The actual amounts produced at CERN are measured in thousands of atoms, a quantity so small it has essentially no mass at all. But even those microscopic amounts reveal physics. The behavior of antiatoms under gravity, which has only recently become measurable at CERN, confirmed in 2023 that antihydrogen falls downward under gravity just as hydrogen does. Before that measurement, it was an open question. Some theoretical extensions of the Standard Model predicted that antimatter might fall upward. It does not. Antimatter obeys ordinary gravity. Each experiment with trapped antimatter closes one possible door. The symmetry holds here, the symmetry holds there. And by process of elimination, the broken symmetry responsible for our existence narrows to specific interactions, specific particle types, specific conditions that only existed in the early universe. The measurement program at CERN continues to improve. New techniques are extending precision. And while the antimatter factories of CERN work at atomic scales, a completely different line of investigation is probing the largest scales in the universe, asking whether entire galaxies made of antimatter might still exist somewhere, hiding at the edge of what we can see. A paperclip weighs about 1 gram. 1 gram of antimatter, meeting 1 gram of regular matter, would release energy equal to an atomic bomb. Not similar to an atomic bomb, equal to it. The complete conversion of 2 grams of mass into pure energy, following Einstein's equation exactly. Every last bit of mass becoming light and heat and radiation, with nothing left behind. The atomic bombs dropped during World War II converted less than 1% of their fissile material into energy. The rest scattered as debris. Antimatter annihilation converts 100%. No waste, no debris, just energy. This is why antimatter has appeared in science fiction as the ultimate fuel and the ultimate weapon for decades. The physics behind it is not fiction. The energy release per gram is real, calculated, and confirmed by the same physics that describes every nuclear reaction ever measured. The math is not in dispute. What makes this relevant to the matter-antimatter mystery is what it tells you about the first second of the universe. The annihilation in those early moments was not a controlled release. It was the simultaneous and total conversion of almost all the mass in the observable universe into radiation. Every pair of particles that met and annihilated released this amount of energy per unit mass. And the universe was doing this everywhere at once. The total energy released by that early annihilation is still present in the universe today. It is the cosmic microwave background radiation, now stretched thin by 13.8 billion years of cosmic expansion, but still there, still measurable, still containing a record of the total amount of mass that was destroyed. Scientists can calculate from the current energy density of the cosmic microwave background how much mass was annihilated in those first seconds. And when they compare that to the current amount of visible matter, they get the ratio. 1 in 1 billion. The number that started this whole story. The energy density of the cosmic microwave background is not a guess. It is measured by satellites with extraordinary precision. The amount of matter currently in the universe is measured through gravitational surveys and galaxy counts. The ratio between the two is one of the most precisely confirmed numbers in cosmology. That ratio is the fingerprint of the annihilation. 1 billion times more energy than matter. 1 billion photons for every surviving baryon. The universe carries the exact ratio you would expect if almost all the matter was destroyed and a tiny fraction survived, confirming that the destruction happened exactly as the theory describes. The energy of the annihilation is frozen in the structure of the universe itself. The cosmic microwave background is not just an echo. It is a measurement. And what it measures, with extraordinary precision, is the size of the asymmetry that allowed everything to exist. What scientists do not have yet is a complete explanation of what caused that asymmetry. The kaon result, the baryon result at the Large Hadron Collider, the neutrino hint from Japan, all point toward the same conclusion. CP symmetry is broken in multiple particle families at multiple scales, but the total measured violations still fall short of the total observed asymmetry. Something is missing. A mechanism, a particle, a process not yet discovered. The next generation of instruments is being built right now to find it. And one of the most intriguing possibilities involves a type of matter so invisible that even after decades of searching, scientists have never directly detected a single particle of it. The universe is mostly something we cannot see. About 27% of the total content of the universe is dark matter. It does not emit light. It does not absorb light. It does not interact with electromagnetic radiation of any kind. The only way scientists know it exists is through gravity. Dark matter pulls on the things around it the same way regular matter does. Its gravitational effects show up in the rotation of galaxies, the bending of light from distant sources, and the large-scale structure of the universe. But the particle, or particles, responsible for it have never been directly detected. Now, here is the question that some physicists are asking. Could dark matter be connected to the matter-antimatter imbalance? The masses line up curiously. The amount of dark matter in the universe is about 5 times the amount of regular matter, 5 to 1. That specific ratio is not predicted by any current theory. It looks like a coincidence. And in science, apparent coincidences often turn out to be connections waiting to be understood. Some theoretical models propose that dark matter and regular matter were both produced by the same mechanism in the early universe. In these models, the same process that generated an excess of baryons over antibaryons also generated an excess of dark matter particles over their antimatter versions. The two asymmetries are linked. They came from the same event, governed by the same physics, and their ratio reflects shared origin. This idea goes by the various names in the theoretical literature. Asymmetric dark matter is one framework. The common thread is the proposal that dark matter has a matter-antimatter asymmetry of its own, parallel to the baryon asymmetry produced by similar or identical mechanisms in the early universe. If dark matter and regular matter asymmetries are both set by the same underlying process, the 5-to-1 ratio between them might be explained rather than assumed. The challenge is that scientists cannot yet test this directly. Dark matter particles, by definition, interact with regular matter so weakly that detection experiments have spent decades searching without a confirmed discovery. The Xenon, LUX, and Pandex experiments, underground detectors filled with liquid xenon designed to catch rare dark matter collisions, have ruled out many theoretical possibilities but found nothing definitive. If dark matter has an antimatter counterpart, that antimatter dark matter should also be present in the universe. Whether there is any difference between dark matter and antimatter dark matter, and whether that difference connects to the baryon asymmetry, are questions that require both a better theoretical understanding of what dark matter is and better experimental tools to study it. Current instruments cannot answer these questions. The next generation might, but the timeline is uncertain, because progress on dark matter detection has been slower than many physicists hoped. What the dark matter connection illustrates is the depth of the baryon asymmetry problem. It does not sit in isolation. It connects to dark matter, to neutrino mass, to the seesaw mechanism, to the thermal history of the early universe, to the large-scale structure of the cosmos. Pulling on one thread moves others. The full solution, when it comes, will likely reorganize multiple parts of physics simultaneously. And at the very edges of the observable universe, an even stranger possibility has been waiting for decades to be ruled out. An idea that, if true, would mean the question of where the antimatter went has the simplest possible answer. What if the antimatter did not disappear? The standard story says matter and antimatter destroyed each other in the first seconds of the universe, leaving only the tiny baryon surplus behind. The antimatter was annihilated. Gone. Converted to radiation. Case closed. But what if some of it escaped? What if, in some regions of the early universe, a slightly different process played out, and large clumps of antimatter survived the annihilation alongside the matter that survived? What if, instead of being uniformly distributed, matter and antimatter separated into different regions before they could fully destroy each other? And what if those regions, separated by the vast distances, then each condensed into their own galaxies? A galaxy made of antimatter would look identical to a galaxy made of matter. Anti-stars burning the same nuclear reactions as regular stars, anti-planets orbiting them, anti-gas filling the spaces between. From a distance, you could not tell the difference. Anti-hydrogen emits the same light as hydrogen. The spectrum of an anti-star is identical to a regular star. There is no flag, no color, no signal that marks a galaxy as antimatter, just by observing it from far away. The only place the difference would show up is at the boundary. If a matter galaxy and an antimatter galaxy ever collided, the contact zone would produce an enormous burst of annihilation radiation, exactly the gamma ray signal that antimatter annihilation always produces, but at galactic scale. A region of sky where two galaxies were merging would glow with high-energy gamma rays, unlike anything produced by normal astrophysical processes. Astronomers have searched for this signal. Satellite observatories designed to detect gamma rays have scanned the sky for signs of large-scale matter-antimatter annihilation happening anywhere in the observable universe. So far, they have found nothing that requires an antimatter galaxy to explain it. The absence of that signal places constraints. Scientists can estimate that if antimatter galaxies exist, they must be separated from matter galaxies by enormous distances, large enough that the two populations have never come into close contact. Given the large-scale structure of the universe, which has galaxies and galaxy clusters distributed across hundreds of millions of light years, the required separation would be so large that it raises its own theoretical problems. Explaining how matter and antimatter could have separated that thoroughly in the early universe requires mechanisms not supported by current cosmological models. The antimatter galaxy idea is still alive as a possibility precisely because it has not been directly ruled out. The gamma ray surveys are sensitive, but not infinitely sensitive. A very diffuse boundary region between matter and antimatter domains might produce a signal too faint to detect with current instruments. The most honest statement of the scientific consensus is that antimatter galaxies are unlikely, poorly motivated by theory, and unsupported by observation, but cannot be completely excluded with current data. Future gamma-ray telescopes with greater sensitivity will push that constraint further. For now, the antimatter galaxy scenario sits in a category alongside other speculative possibilities, not disproven, not ignored, and not a productive place to focus the main search. The evidence that CP violation in quarks and neutrinos is the key point much more strongly toward the mechanisms being hunted in underground detectors and particle accelerators. But the question stays open. And in physics, open questions are invitations. The next generation of instruments is being built, and what they find in the coming decade will determine which of these ideas survives and which disappears. The answer is coming, just slowly. Physics moves on the timescale of decades. An experiment is proposed. Funding is secured over years of negotiations. Construction begins. Detectors are assembled with components manufactured across dozens of countries. The machine is commissioned, tested, and calibrated. Data collection starts. Years of data accumulate. Analysis runs. The result is published. From proposal to publication, a major particle physics result can take 20 years. But right now, several projects are at or near the data collection phase, and what they produce in the next decade is expected to either confirm the neutrino explanation of the matter, antimatter asymmetry, or force physics to look somewhere new. Hyper Kamiokande is the successor to Super Kamiokande in Japan. Construction is underway in the same Kamioka Mountains, in a new cavern carved from the rock nearby. The detector holds 260,000 tons of ultra-pure water, more than 5 times the volume of its predecessor. The T2K beam from Tokai will send neutrinos and antineutrinos toward this vastly larger detector. The increased volume means more neutrino interactions per year, more data, and faster accumulation of the statistical certainty needed to either confirm or rule out large CP violation in the neutrino sector. DUNE, the Deep Underground Neutrino Experiment, is under construction in the United States. A powerful neutrino beam will be generated at Fermilab near Chicago and fired 800 miles through the Earth to a detector in the Sanford Underground Research Facility in Lead, South Dakota. The detector uses liquid argon rather than water, a technology that provides more detailed information about each neutrino interaction. The longer baseline of 800 miles compared to T2K's 183 miles gives DUNE sensitivity to different aspects of the oscillation pattern, making the two experiments complementary rather than redundant. At CERN, upgrades to the Large Hadron Collider and its experiments are being implemented. The upgraded LHCb detector has improved resolution and will collect data on baryon decays at higher rates than before. More data on Lambda B and other baryons will refine the measurement of CP violation in the baryon sector and potentially reveal violations in additional baryon types not yet studied. A proposed next-generation collider, the Future Circular Collider, would be a machine roughly 3 times the circumference of the Large Hadron Collider, capable of reaching energies far beyond what is currently accessible. At those energies, particles that today exist only in theoretical equations might become experimentally accessible. The decision on whether to build it has not been made, and construction would take decades if approved, but the planning work is already underway. In parallel, theoretical work continues. Every new experimental result feeds into calculations that constrain which models of leptogenesis are still viable, which extensions of the standard model remain consistent with data, and which predictions each surviving model makes for upcoming experiments. The convergence of Hyper Kamiokande and Dune results, expected sometime in the 1930s, will be a defining moment. 2 independent experiments, both measuring neutrino CP violation, their combined data either crossing the 5 sigma threshold and confirming the mechanism, or showing the signal was a fluctuation and forcing the field to pivot. Either outcome changes everything. A confirmation would mean humans have identified the mechanism that allowed matter to survive the Big Bang. A null result would mean the answer is still hidden, waiting in some corner of physics not yet reached by any instrument. The machines are running, the data is accumulating, the clock is moving. Imagine the moment the result is confirmed. A team of physicists, gathered around a display of statistical curves in a conference room deep inside a mountain in Japan or beneath the plains of South Dakota, watches the data cross the 5 sigma threshold. The signal is clean. The result is real. Neutrinos violate CP symmetry at a level that, combined with the leptogenesis framework, accounts for the observed matter-antimatter asymmetry of the universe. The mechanism that allowed you to exist would be identified. The scientific implications radiate outward in every direction. Leptogenesis would shift from a compelling theory to a confirmed mechanism. The standard model, already known to be incomplete, would need a concrete extension to include the heavy right-handed neutrinos that the theory requires. Those neutrinos would have masses so extreme that no collider could produce them directly, but their existence would be inferred with confidence from the confirmed behavior of their light descendants. The connection between neutrino mass and the origin of matter would be established. The smallness of neutrino mass, the fact that the lightest particles with mass in the universe are almost massless, would be understood as a consequence of the same process that decided whether matter or antimatter would dominate the cosmos. 2 previously separate puzzles solved by a single mechanism. Dark matter models that link the dark matter abundance to the baryon asymmetry through a shared production mechanism would gain new support if the leptogenesis pathway is confirmed. The 5-to-1 ratio of dark matter to regular matter, currently unexplained, might find a natural home in the same theoretical framework. For physics education, the impact would be deep. The current textbook treatment of the matter-antimatter asymmetry ends with an open question. A confirmed mechanism would close that question and open new ones. How do the heavy neutrinos connect to grand unified theories? What broke the symmetry at an even deeper level? Is leptogenesis the complete story, or a chapter in something larger? For the general understanding of humanity's place in the universe, the confirmation would carry a different kind of weight. The question of why anything exists, why the universe contains matter rather than dissolving into radiation, has an answer that reaches into the daily life of every person alive. Every atom in your body is there because of a specific physical mechanism that operated in the first fractions of a second after the Big Bang. Knowing that mechanism, not just in outline but in confirmed detail, is knowing something fundamental about your own origin. Science rarely produces moments that deserve to be called revelations. Most progress is incremental. One measurement refines another. One theory extends the previous one. But occasionally, a result lands that reorganizes how humanity understands its position in the universe. The confirmation of leptogenesis would be one of those moments. It would not answer every question. The origin of the heavy neutrinos themselves, why they have the masses they do, why the CP violation in their decays is the size it is, would remain open. But the chain from those decays to the matter in your bones would be closed. And closing it would be one of the most profound scientific achievements in human history. Knowing why matter exists and being able to control it are two different things, but they are not unconnected. The history of physics is the history of understanding becoming technology. Maxwell's equations describing electromagnetic waves became radio and radar. Quantum mechanics, initially pure mathematics about atomic behavior, became the transistor, the laser, and every electronic device in existence. Nuclear physics became power generation and medical imaging. The pattern repeats. Deep understanding of the rules of nature becomes the ability to engineer reality at a new level. If the mechanism of the matter-antimatter asymmetry is confirmed and fully understood, what does that open up? The most immediate application is precision. Understanding exactly how CP violation operates in neutrinos and how that connects to the conditions of the early universe would allow physicists to calculate the full parameter space of the Standard Model extension that includes heavy neutrinos. Those calculations connect to predictions about other rare processes that should be measurable with near-future instruments. Confirming those secondary predictions would validate the entire framework with a depth that extends far beyond the single measurement that triggered it. At a more speculative but scientifically grounded level, the ability to produce and control antimatter precisely, already beginning through the CERN anti-hydrogen program, connects to transformative technologies. Antimatter propulsion for deep space travel is a legitimate concept in physics. The energy released per gram of annihilation fuel, compared to the best chemical or nuclear rockets, would reduce travel time across the solar system from years to weeks. The engineering challenges of producing and storing sufficient antimatter are enormous, but they are engineering challenges, bounded by practicality rather than fundamental physics. Antimatter as a medical tool is already here, in the form of positron emission tomography scanners. Understanding the deeper physics of antimatter interactions might open new medical applications. Higher energy antimatter interactions with tissue destroy cells at precise locations, an idea already being explored in cancer treatment research as a more targeted alternative to conventional radiation therapy. There is also a foundational implication. If scientists understand the mechanism that set the matter-antimatter ratio of the universe, they understand a constraint that shaped every subsequent event in cosmic history. Every star that formed, every planet, every chemical element heavier than helium, all of it traces back to that first asymmetry. Understanding the asymmetry is understanding the initial conditions that made complexity possible. Some physicists speculate further. If the laws of physics allowed a different asymmetry, a universe with 2 particles surviving per billion rather than 1, would stars form differently? Would the elements be distributed differently? Would the conditions for chemistry and biology arise? These are questions at the edge of what can be formulated scientifically, but they point toward a deeper question about whether the specific asymmetry our universe produced was inevitable or contingent. The knowledge of what happened does not give immediate control over it. The conditions of the early universe, the temperatures and densities required, are not reproducible, but understanding the mechanism places humans in the position of knowing the rule rather than just experiencing its consequence. And in the history of science, knowing the rule has always eventually led somewhere unexpected. The universe broke its own rules once. The question is whether it stopped there. CP symmetry was supposed to be perfect. It was not. The assumption that matter and antimatter were interchangeable was built into the foundations of physics. Confirmed by every experiment up to 1964, and then quietly shattered by Kaon's decaying wrong in a windowless room on Long Island. The rule that should have guaranteed an empty universe was broken, and the crack in it is the reason everything exists. That one broken rule raises a question that physicists rarely ask out loud but cannot ignore. What else is wrong? The Standard Model is the most tested theory in the history of science. Its predictions have been confirmed thousands of times across dozens of experiments on multiple continents. It is extraordinarily accurate, and it is demonstrably incomplete. It cannot explain gravity at the quantum level. It has no dark matter particle. It cannot account for dark energy. It underpredicts CP violation by factors so large the discrepancy is not a rounding error, but a foundational gap. An incomplete theory means missing rules. Rules that the universe is following but that humans have not yet written down. And missing rules means that somewhere, right now, processes are happening in nature that do not fit the current model. Particles behaving in ways the textbooks do not describe. Forces operating at scales too small or too large for current instruments to reach. Symmetries breaking in places not yet observed. The history of physics is full of moments when a rule believed to be absolute turned out to be an approximation. Newtonian gravity worked perfectly for centuries, until Einstein showed it was a simplified version of something deeper. The atom was thought to be fundamental until the nucleus was discovered inside it. The nucleus was thought to be fundamental until quarks were found inside the proton. Each layer of the universe, when examined at finer scales, reveals structure where none was assumed to be. The matter-antimatter mystery sits at exactly that kind of boundary. Current measurements show CP violation in multiple particle families. Each measurement is real and confirmed, and yet the total falls short of explaining the universe. The shortfall is not a measurement error. It is a gap in the theory. Something is missing. That missing piece might be the heavy right-handed neutrino of leptogenesis, too massive to produce in any accelerator. It might be a new force operating at scales beyond what any collider has reached. It might be a broken symmetry in a sector of physics not yet imagined. The gap does not specify what fills it. It only confirms that something does. The universe broke CP symmetry quietly, in fractions of a percent, in the decays of kaons. Then it broke it a little more in B mesons and in lambda B baryons. Then it hinted at breaking it far more dramatically in neutrinos. Each discovery pointed deeper. Each answer led to a larger question. The pattern suggests that the universe does not follow a single clean rule. It follows a stack of rules, each one an approximation of something deeper. And every time humans dig down one level, the next level reveals something stranger and more fundamental waiting below it. We are one level down from where we started. The 5 sigma confirmation of the neutrino CP violation, when it comes, will be another level down. What is below that level, no one currently knows. The universe broke its rules to let you exist. The search for which rule it is breaking right now, quietly, in places not yet instrumented, is the frontier of physics. And it will not stop being the frontier until there are no more levels to find, which, given the pattern so far, seems like a very long way away.